Figure 1 shows a stationary wave of a vibrating spring. Give the number of complete wavelengths shown on the spring in Figure 1. Remember that we've got a node there and a node there, and the distance between nodes is half a wavelength. So that's half a wavelength, that's one wavelength, that's 1.5, and that's 2 wavelengths. Add a letter X to the figure to show the position of one antinode. Remember, antinode is in the middle between the two nodes, is the point that oscillates to max amplitude. So you could have an X there, you could have an X there, or you can have an X there or there. Any one of those. Just one antinode you're asked to do. Which process causes the stationary wave on the string in Figure 1? Well, of course, it is resonance. So when half a wavelength or a multiple number of half wavelengths. The string in Figure 1 is 1 meter long, so you're given the length. The mass of the string is 2.1 grams. Remember, whenever you have mass, it must be converted into kilograms. So I'm going to do that to start with. So mass divided by 1,000 is 0.021 kilograms. The tension in the string, that's given the symbol T, is 3.6 newtons. Calculate the speed v of the wavelength of the string in Figure 1. Use the equation. That speed is the square root of tension over the mass per unit length. So the mass per unit length is the mass of the string divided by the length, and it is in kilograms per meter. So of course the mass per unit length will be the mass of the string divided by the length of the string, which is 1 meter. So the mass per length is 0.021 kilograms per meter. And you'll get 2 marks for working that out by converting and doing that. And finally, the speed is the square root of tension over mass per unit length, which is the square root of 3.6 divided by 0.021. And that gives you 41 meters per second. String instruments such as guitars produce a range of musical notes. Changing the tension on the string is one factor that can alternate the pitch of notes. Give 2 other factors that can be changed to alter the pitch of notes that the strings produced. Remember to read the question carefully. So many candidates write the tension when they've already been told it. So of course, if you change the length of the string, that's going to change the pitch. And secondly, the thickness of the string change the pitch, which is because of the mass per unit length. Figure 2 shows a transmitter, satellite and receiver in a communication system. Before you read the question, have a look at the diagram here. You can see that when we use microwaves, we have to transmit a signal up to the satellite. That's called an upload or uplink. And remember, as it's traveling through the atmosphere, it's going to lose energy with an inverse square law. So it's going to be quite weak when it gets here, which means it has to be amplified, and then it goes on a different frequency, the download or downlink frequency, which has a different frequency to stop interference, and it will have to be amplified here. And the advantage of microwaves over radio waves is if this is the ionosphere or the atmosphere, microwaves can travel through the atmosphere, whereas radio waves cannot. They're absorbed or reflected back by the ionosphere. And also microwaves have a higher frequency than radio waves, so therefore can carry more data per second as they have a greater bandwidth. So a microwave signal is uploaded to the satellite from a transmitter on Earth. The satellite transmits a new microwave signal. The new microwave signal is downloaded to the receiver on Earth. Which statements about microwaves is correct? Well, microwaves are transverse, not longitudinal, so that's wrong. Microwaves travel at the speed of light in a vacuum. They do because they're electromagnetic wave. All of them travel at the speed of light. So it is that one. Explain one advantage of using microwaves to carry the signal from a satellite communication. Well, the key one is that microwaves pass through the ionosphere. Microwaves can pass through the atmosphere, ionosphere, so can travel to higher orbiting satellites. The upload signal received at the satellite is different from the download signal transmitted from the satellite in frequency and amplitude. So reading the information carefully really helps. Give one reason why the upload signal and download signals have different frequencies. That is to stop interference. Secondly, give one reason why the satellite needs to be amplifying the uploaded signal. Well, the key one is because the signal is weak. Question 3. A microphone converts sound waves into electrical signals. Figure 3 shows an analog signal from the microphone. Notice it's varying continuously with time and times in milliseconds, and the voltage output is the amplitude, and that's in millivolts. Give the maximum voltage of the signal in figure 3. Now, what you need to do is to check your scales here, because you've got 5 squares in 2. So 2 divided by 5 is equal to 0.4. So if you have a look here, it's 14.48, exactly 15. The mark scheme allowed you 14.8 to 15.2. Figure 3 shows an example of an analog signal. Complete the sentence 1 for the correct definition of an analog signal. The signal in figure 3 is an analog signal because it's the output voltage, or the voltage, varies continuously with time. Part C. Describe how an analog signal can be converted into a digital signal. Well, what you need to do is, first of all, you need to sample at set time intervals. So you can see I am sampling at set time intervals of 0.2 milliseconds. And once you've sampled at a set time interval, you then convert that voltage from an analog signal into a digital binary code or number. So this is what I would say. The signal is sampled at set time intervals. The voltage is then converted into a binary digital code, which is a digital signal. Question 4. Which diagram correctly shows the refraction of light when passing from air into an optical fibre? Well, of course, when light passes from air into an optical fibre, it slows down and bends towards the normal. So that's the normal, it's going to be C. The speed of light in air is 3 times 10 to the 8. The light passes into an optical fibre. The refractive index of the optical fibre is 1.55, that is n. Calculate the speed of light in the optical fibre V. Use the equation n equals c over v. In the latest exams, they have been quoting you the equation in the question rather than you having to look at the back, but there are the equations on the back. So first of all, I've got to rearrange it for v. So make sure that if you're not very good at rearranging equations, you put it in a triangle first, you don't lose that mark. So c must go on top because v is underneath c, which means n must go there in the triangle. So v is equal to, cover up v, it's c over n, c divided by n. C, of course, is the speed of light, and that's 1.55, and that gives us 1.9 times 10 to the 8 meters per second. The last question is a 6-mark question. It says a doctor uses a medical endoscope to see inside the stomach of a patient. Figure 4 shows the medical endoscope inside the stomach of a patient. Medical endoscopes contain optical fibres. So you can see it has to transmit light down and then light has to come back up. Explain how the optical fibres transmit light so the doctor can see inside the stomach. You may include annotated diagrams to support your answer. So before you put pen to paper, think very carefully about what you're going to say. First of all, you've got to have two different bundles of optical fibre. The first bundle of optical fibres gets the light down into the stomach to illuminate the stomach wall. Those are the cheaper types of bundle because they don't have to be coherent, which means they can all be jumbled up. They've just got to light this area. But light reflects off the stomach wall and comes back along a separate bundle of fibre optics, and those have to be coherent, that those fibres must be parallel and in the same orientation up here as down here, because each fibre acts as one pixel, so produces light for one pixel, so your image is not jumbled up. So that's what the two fibre optic bundles do. How does light transmit itself down a fibre optic and back? Of course, that's by total internal reflection, because the angle of incidence is greater than the critical angle. And of course, that will only happen if light is trying to go from a more optically dense to a less optically dense medium, or trying to speed up at the boundary. And finally, you could mention the cladding, which is on the outside of the bundle to stop light from one fibre optic crossing over into another fibre optic. I would also draw a diagram briefly to illustrate as well. So I'd start with the basic key things about how light travels down a fibre optic. Light travels down a fibre optic by total internal reflection. This occurs when light is travelling from a more optically dense to a less optically dense medium, speeding up, when the angle of incidence is greater than the critical angle. The next part of the answer is to talk about the difference in the fibre optics sending light into the stomach and the fibre optics transmitting the light back. Light travels into the stomach down a bundle of non-coherent optical fibres. They are jumbled up. Light reflects off the stomach wall and travels back along a different bundle of optical fibres. These optical fibres need to be coherent, not jumbled up. Each fibre acts as a single pixel. So fibres at the top need to have the same orientation, pattern, as at the bottom to produce a clear digital picture.